MATLAB, Tyler can help you out with the MATLAB if this isn't sufficient for you. But everybody should do this homework in MATLAB. You should write your own code. You can work with other people if you need help. The first thing we want to do is make a function. The function is we're going to give it a current, how much current we're injecting into the neuron through an electrode. So that's the current. And then we're going to rig what the voltage comes out. We're going to integrate a bunch of equations to the Hodgkin-Huxley equations to get the voltage as a function of time. Okay? So the function out comes voltage and the time base, and then the function I called Tay Hodgkin-Huxley equations, and we're going to put in a scalar, which is going to be have to do with the current. And you're going to have to figure out how much current. A lot of current's going to make the neuron do one thing. Very little current's going to make it do nothing. Okay, so in MATLAB, comments are in parentheses or in percent symbols. So the comment at the top just sort of tells you what this function is. I'm going to need some coefficients. We're going to use more and more coefficients, like you might add in coefficients, which is this resistance along the axis and things like that, which we're going to play with those values a lot. So I tend to make a structure, and I make a structure called coefs, which keep all of the parameters of my model that I like to pass to the model, that I don't put explicitly in it. We need to set initial conditions. So I set the voltage initial condition to something around the reversal potential, minus 60 millivolts. I set the activation, sodium inactivation, and potassium activation to some initial condition. It has to be between 0 and 1, and usually I set it at 0 to start. And then you have to make that into a vector. So you can only integrate one thing when you run a differential equation integrator. And so when you want to do multiple equations to calculate dv dt, dm dt, dh dt, and dh dt, you have to make it into a four-dimensional vector. So we will concatenate those into a vector. And I always get it wrong if they're supposed to be a row vector or column vector. So these are the kinds of things. This is pseudocode. It's not real code. You'll have to figure out those details. If the model tells you this doesn't work, then try putting semicolons in between. Okay, and then you have to specify the start time and the end time of the simulation. So you can specify just an array of two values. The start time, usually I started at time 0 and end at time 1,000 if I want to go for 1 second. So these are all in milliseconds. And I would recommend doing at least 1,000, if not 10,000 milliseconds in your simulation. And then, or you could actually specify a bunch of points at the time, and the model output the values at each one of those time points. Otherwise, it'll figure out what the optimal time step is, depending on a variable time step integrator. And then you have options, and the options we're not going to discuss yet. Then you have this function called ODE15S. And ODE15S is the integrator. What it needs is a function that tells you what the differential equation is. So the input to the function, and that function I called calc_derivs. And in MATLAB, you can actually put that function within another function. So you can see down below, you see two plots. A long comment, two plots. There's a thing called calc_derivs. That's my function that calculates the derivatives. The first input to it is time. The second one is the states of the system. That's that vector that we start with the initial conditions. The third one is the input current. So that's something I'm going to play with in my simulations. I'm going to pass directly into my Hodgkin-Huxley function. And then the third one is coefs. You can make as many things after as many coefficients you want, or arguments as you want. But the first one has to be time, the second one has to be state. Because I don't like things in vectors, the first thing I do in that is I rename everything. So the first value in S is the voltage. The second value is the sodium activation, M. The third one is the sodium inactivation, and the fourth one is the potassium activation. So that makes all my equations look pretty. Then I go through and calculate alpha m's. So I go and write in the equations. They're in the homework. Alpha m's as a function of voltage, Actually, I have it wrong there. I just wrote V, and up above I wrote VM. So this is pseudocode, not real code. Then you calculate the beta M's, alpha H's, beta H's, alpha M N's, beta N's. And then you have to calculate, now that you have all the alphas and betas, you calculate the M imps, the N imps, the H imps, the tau imps, the tau m's, the tau h's, the tau n's. And then you calculate dn dt given the m inf minus m over tau m. You calculate dh dt, d mdt, and then you calculate dv dt, which is -1 divided by the capacitance times, and then you sum up all the coefficients. So you calculate n times G max times n times v minus ENA, right? And the equation raised to the fourth, right? This equation, you put this equation in, that will be the sodium. You put this equation, you'll put the one for the leak, and then whatever your current is for your electrode. And that calculates the dVdt, and then you have to put everything back into a vector again. So ds dt is equal to a vector. The first value has to be the exact same thing as the first thing in your initial conditions. dv dt, dm dt, dn dt, dh dt. It has to be either a row or column. I can never remember. So ODE15S will keep calling. It will give it a new voltage, give it a voltage. It will calculate dv dt. It'll calculate how much change to the voltage, and then it will start over and just keep calling this dv dt thousands and thousands of times until it comes to the conclusion of your simulation. And at the end, you just plot t times v. That's the output of your ODE15S. If you plot t and v, you'll get, because it's 4 dimensions, you'll get four lines that come out. One of them representing v, one m, n, and h. Your m, n, and h never go below 0 or above 1. If they do, something's wrong with your equation. So you have a minus sign wrong someplace. You have to figure it out. And that's it. So it's just a matter of popping these things into MATLAB and calling it from MATLAB.